Started. So today we're very pleased to have Mark Leicester here to give our seminar. Mark is a professor at the University of Leicester, where his research interests include exploring the plasma and ionospheric dynamics at both Earth and Mars. Mark is a key contributor to the community, as well as leading the International SuperDARN project from 2004 to 2019. Mark has also held numerous roles within RAS Council, most recently being the RAS Secretary. These contributions have been in part recognised, with Mark receiving the RAS Award for Services to Geophysics in 2014. Today, Mark is going to be speaking on spacecraft observations of the Martian Ionosphere. So I'm going to hand it over to you now, Mark.
Thank you, Jasmine, and hello, everyone. Thank you for joining the seminar this morning. So my title is slightly different from that Jasmine gave. It's going to talk about sounding the Martian ionosphere. And we're going to look at data primarily from Mars Express, but also with other satellites at Mars as well. And I should like to acknowledge the support and contributions of a whole host of other people there, a number of my colleagues at Leicester, as well as people elsewhere in the community. And there are others that whose name I haven't added on here, which is just an oversight on my part. So my outline is very simple. I will introduce the Martian plasma system because I'm aware that not everybody will fully know about that. Give us a quick overview of Mars Express, explain how MARSIS operates and the sort of data products that we can get, give some of the science highlights, and then just look to the future a little bit at the end. So I'm going to start by thinking about the Mars plasma system and in terms of the interaction between the Martian environment and the solar wind. And this is just a fairly standard plot that we see for all planetary systems. Normally you have a magnetic field which is extending out into the solar wind in some way, holding off the solar wind. But there's no dipole field at Mars, and that means that the solar wind interacts directly with the atmosphere and ionosphere. It's a highly variable and very diverse plasma environment, I should say. And you do get what people refer to as induced magnetospheres around here, but you can see the green line here is the bow shock, and then across that you have a magnetosheath region where the solar wind is slowed. You get magnetic pileup as you approach as the solar wind approaches the planet, and it leads to this boundary called the magnetic pileup boundary, which is sort of a boundary between the sheath and any internal induced magnetosphere or the ionosphere. One thing that Mars does have are these crustal fields, often considered to be just remnants of the old of the original dipole field that the planet used to have. But this results in a varied interaction with the IMF, of course, potentially under certain conditions, the interplanetary magnetic field, or at least the sheath field, can reconnect with that and cause open field lines dragged back into the magnetotail, or of course you get closure of magnetic field lines in magnetotail down here. We also see, for example, in this part, you see regions of high ionization being transported into the tail. But there are regions which we certainly have no idea about. For example, this region down here is mostly unexplored. So we know fair bit now about the structure, certainly close to the planet, but the dynamics is yet to be fully resolved. Now I'm going to switch the perspective and think about this now from the bottom up, the interaction of the atmosphere with the plasma environment. Now, Mars' atmosphere and ionosphere, we know, are indeed highly variable. Because the planet is irradiated by our sun, you get a main layer being created, which is very Chapman-like, the so-called M2 layer, which peaks at around about 140 to 150 kilometers, sometimes a bit lower than that. There's also a somewhat sporadic secondary layer, although the formation of that is still to be debated and is really not as well understood. And then there are these meteoritic layers, mainly through magnesium plus ions, which form lower down. And this is on the day side now. This is the left-hand panel. On the night side, you still have often an ionization in the M2, depending on exactly where you are in the tail. This is probably due to a mixture of transport, possibly electron precipitation, and primarily you see this near the terminator, but as we'll see, you can actually get layers being created quite deep into the round on the night side. Again, you still have that meteoritic layer, but most importantly, what we're actually now finding is that the atmosphere interacts much more strongly with the ionized regions than perhaps we see at Earth. It can do so through dust, the impact of the dust on the upper boundaries of the system, and through gravity waves. You have some very high mountains, as you know, at Mars, and also through chemistry, and I'll talk a little bit about that later on. Mars Express was launched on the 2nd of June 2003, so we're just a month away from its 20th anniversary. And its orbit insertion at the red planet was on Christmas Day 2003. And most of us at Leicester remember that day as a day of disappointment, because of course that was the day that Mars Express also let Beagle 2 land on the planet. But unfortunately, the solar panels didn't deploy properly. Fortunately, Mars Express has continued to operate, and from a nominal 2-year mission at Mars, which it's now been extended by the European Space Agency, and recently we heard, and thanks to everybody who signed the letter of support, that this is now going to operate until at least 2025, with the likelihood that it will continue to 2028. Now, the payload has a number of instruments for plasma physics, and the 4 here are the 4 that I'm most familiar with, and I'm only going to talk about the top data from the top 2 today. The first is the Analyzer of Space Plasmas and Energetic Atoms, ASPERA 3. This is a low-energy plasma, electrons and ions, as well as neutral atom instrument. The Mars Advanced Radar for Subsurface and Ionospheric Sounding, MARSIS, which is the instrument that I'm going to talk about in quite a lot of detail. There's another radio science mission, the Mars Express, instrument, the Mars Express Orbiter Radio Science. This is a radio science instrument that does occultations of the Mars Express signal back to Earth, and using those occultations through the atmosphere and ionosphere, you can get characteristics of the ionosphere and indeed the neutral atmosphere, density and temperature of the neutral atmosphere, but this is much lower down. This is below the ionization, the peak of the ionosphere. The interesting thing about MRS is that we're using data from MRS, that this M1 layer that has been postulated. There's also an instrument, SPECAM, spectroscopy for investigation of characteristics of the atmosphere of Mars, which was the first instrument at Mars to show that Aurora was present. And I will talk a little bit about that, but from some more recent observations. MEx orbit has a 7-hour period about the planet. Its periapsis is close, somewhere between 300 and 400 kilometers, and it has an apoapsis of about 10,500 kilometers. And that's about 3.3 Martian radii from the surface. So it does spend a fair bit of time in the solar wind when the apoapsis is on the day side. The MARSIS instrument operates in 2 modes, and both modes provide data which can be used for the sort of science that we're all interested in. The main mode, main operational mode, is its subsurface mode. This is looking effectively for water beneath the surface of the planet, which indeed it has, it's suggested it has found. And in the subsurface mode, it operates at a fixed frequency, typically 3, 4, or 5 megahertz, reflects from the surface, but also, of course, the fact that it's the signal will propagate into the surface means that you will get information from those subsurface regions. The other mode is the advanced ionospheric sounder mode. It's a topside ionosonde. An ionosonde is a fairly routine instrument which is used at Earth to probe the bottom side of the Earth ionosphere. Because this is on a spacecraft, we're looking purely at the top side. We scan between 0.2 and 5.5 megahertz, producing topside ionospheric density profiles. And currently, the University of Leicester is responsible for the operational planning for AIS, as well as the data pipeline. Now, the data products are given on the right-hand side. In subsurface mode, which is really just probing down to the surface and back again, a side product of the analysis is that you can calculate the total electron content along the path. And this is very similar to the sorts of instruments like altimeters on some of the old spacecraft. ERS-1, for example, is one. So you have this particular data product. In addition, of course, if you don't see the surface, then there may be reasons why that is. And one reason for that is that there is absorption of the signal between the spacecraft and the surface and back again. And I'll talk in detail about some of the work that we've done on that. The advanced ionospheric sounder, primarily, we get the topside ionospheric density profile, so a density profile against altitude, more or less from the spacecraft altitude to the peak density. We can calculate the peak electron density as well as the altitude of the peak. But again, if you've got, you do see a surface signal, the absence of that surface signal may be a sign of absorption again. And also, as I'll explain later, you can also estimate the local magnetic field magnitude as well as the local plasma density. When I say local, I mean at the spacecraft. So this is the left-hand panel here is just an example of a plot taken from the Planetary Science Archive of the subsurface mode data. You can see that although it's operating only at single frequencies, it's got a number of different panels, and these are side products of the way the analysis has been done. but effectively what you have is a time delay against a long track distance. So that's just universal time, if you like, and you can see the signal is just in that grayscale. There seems to be a rapid change at, I guess, around about 3/4 of the way along the along track distance. That's purely due to a frequency change. So what you're seeing there is a change in the background noise levels, if you like. The right-hand side is the total electron content from the subsurface mode. That is in that data. Now, what this actually shows is that there are a couple of different methods for retrieving the data, which I'm not going to go into here, so-called Cartacci mode and the so-called Mugino mode or retrieval. And they give us somewhat different estimates, especially as you go, as the density increases. The Cartacci mode is the red line, the Mugino line is data are in the black dots there. And this is work that Beatrice did some years ago, where she compared these observations with some AIS data, just looking at the topside data. Those are the blue stars. Similarly, the AIS data from the purple stars, and then comparing with the NE Mars model. That's the light blue dot, that's the full ionosphere, and the green dots are the topside ionosphere. And basically what you see is that whilst the two estimates of the model do converge as we get to very low solar zenith angles, effectively when we're onto the night side, you can clearly see that there's a difference of maybe anywhere up to a factor of 2 or even larger between the two estimates. But that the Cartacci mode may agree better with the NE model, whereas, and indeed, it looks as if the Mugino model is not quite predicting the full amount of the ionosphere. Now, this is a topic of a lot of controversy at the moment, and we still can't get the proponents of each model together, despite the fact that we've been trying to do that for the last decade or more to talk about this. These are the blackouts that I was talking about. So again, top panel is the MARSIS data. The bottom 3 panels are data from SHARAD, another subsurface operating mode. And in the top panel, what you see is a normal signal. On the left-hand side, a radar blackout in the middle, where you actually have no signal, and then what we refer to as a partial blackout, which is a very, very weak signal, and sometimes, especially after the frequency change, absolutely no signal at all in the MARSIS data. And I'll talk more about that later. This is an example of the AIS mode data. This is an ionogram. We go from the top panel is at 0 to 0, sorry, the top of the left-hand side, the top of that is 0 milliseconds, and it increases downwards to 7.2, 7.3 milliseconds at the bottom. Frequency is on the x-axis, increasing from 0.2 to 5.5 megs. Now, what we see here is basically how this works is it sends out a signal at a given frequency, receives the signal back, and then after a certain amount of time, it sends out another frequency at the next step, an increased frequency, and gets the signal back. So you're sweeping through that frequency and you're receiving all of these signals. So to decode these signals, the first thing to notice is the main trace. That's this trace here. That's the main ionospheric trace. And this is a fairly standard ionospheric trace where the time delay increases as you go to higher frequencies. You're reflecting from different altitudes as you go down until you get to the peak frequency, which is here, and this is the peak of the layer, if you like. This element, the surface signal reflection on the right-hand side, that's the surface signal. You can see that the delay actually increases for the surface signal, which you wouldn't normally expect, but that's an effect of the propagation of the signal through the ionosphere. So actually this increased delay at the lower end of that band would be expected because of the increased delay at those frequencies. And this is one of the reasons, of course, why in subsurface mode you operate at these very different frequencies, so that you can remove the impact of the ionosphere. Then this signal, the off-nadir trace, is simply an off exactly what it says. It's an oblique echo, if you like. And that comes about, of course, because the antenna that we're transmitting from has a very broad transmitting band, and so it can come back from very different regions. And as often what you see is that this trace moves towards the main trace and then away as the spacecraft moves over some feature. And these are often related to regions of strong magnetic field. Then you've got these harmonic lines. You've got the horizontal harmonic lines, which are the electron cyclotron frequency harmonics. That gives us the local magnetic field magnitude. And you've got vertical lines, which are quite difficult to decode in this particular image, but they are there, and that gives us these are harmonics of the plasma frequency, and this gives us local electron density. And these are stimulated simply by the impact of the radio signal with the local plasma at that region, and creating these signals. So this is the ionogram, or this is the profile that we would expect to see. The blue dots are from that trace. The blue dots are the electron density profile. The orange curve is a Chapman fit. We have a peak density of about 1.2 times 10 to the 11 cubic meter and an altitude of order 150 kilometers. So it's taken me quite a long time to get through that. Let's take you through some of the data. And this is some data where we looked at the annual variability of the total electron content. Now, one of the things about Mars, which you must remember if you're looking at ionospheric data, is that the Martian orbit varies quite significantly in terms of its distance from the sun. And so we're going to look at the data as a function of solar longitude as a proxy for the Martian year. Now, the question is there any behavior associated with this variability? What we would expect to see is a fairly simple, hopefully, sinusoidal curve. So let's have a look at the data. The bottom panel is the heliocentric distance. Aphelion is at about 1.67 AU. Perihelion is about 1.4 AU. And you can see that it has a very clear sinusoidal behavior. If we look at the panel above that, we've calculated the irradiance at 30.5 nanometers. And this has been measured by time to Earth using the SEE instrument, and then range corrected for the distance to Mars. And you can see that the estimates of the irradiance, which of course is primarily the function that, or the parameter that would create the ionized layer, that has also a fairly simple sinusoidal curve. So what does the total electron content show us? Well, the total electron content is the top panel. We see that it does have a peak close to perihelion. And this is now just data at solar zenith angles of about 85 degrees. But When we look at aphelion, just before aphelion in this region, between about solar longitudes of 20 and 60 degrees, we see a secondary peak. And we don't understand, well, we didn't understand why that was when we first saw it. But actually, if you look at the pressure curve, the surface pressure curve, it gives you the clue that you need. Now, the surface pressure curve tells you something about just simply the pressure at the surface over the Martian year. This is from MSL REMS instrument. You have a peak at perihelion, you have another peak at aphelion. So there is a very clear double peak structure. Now, atmospheric, that's just the surface pressure. That has to be atmospheric pressure. So atmospheric pressure goes up, must have something to do with the density. And when we look at the column density at say, a given altitude, like 140 kilometers, we see that there is this secondary peak here. And then using the Mars Climate Database, again, looking at the different constituents, we see that in that time frame, oxygen is the peak contributor, whereas at this time, in this time frame, it's become hydrogen. So you've got this very different chemical behavior here. If we look at the contribution of each species, however, to the total electron content, which we've done using this model IPIM and a GCM, then we find that the largest contribution to the TC comes from the O2 plus ion, and that varies between about 77 and 82%. It looks like it's 100%, but remember this is a logarithmic curve, and that's the starred lines here. The green diamonds are O plus, and that peaks here, but CO2 plus peaks over here. And this is a relation of this of the carbon dioxide cycle. And the carbon dioxide cycle comes about because of sublimation of the polar caps. And if we look at the SPECAM data, you see that we have a cyclic behavior in the oxygen species that agrees well with our ionospheric observations and modeling. So this is a very direct impact of the lower atmosphere on the thermosphere. Effectively, not so much the lower atmosphere, but actually the surface and even, if you like, the subsurface. It's really a very interesting aspect of the system. So I'm very briefly going to go through the ionophores at Mars. There's a lot of work that's been done on this, but our work focused on using two particular characteristics. This is now using MAVEN data, but two particular characteristics: a rapid change in electron density with altitude and an increase in the electron temperature variability. One of the things here that we find, and what we've got here is data where there is no ionophores, and this shows the blue curve is the electron density, the red curve is the temperature, pink curve, and the left panels are with an ionophores, and you can see a rapid change in the density here, and this feature of the variability in the electron temperature. And again, here, the top two panels are far from strong magnetic fields, and the bottom two panels are over the magnetic fields. We find that 45% of the deep dip campaigns profiles that we looked at showed an ionosphere. Only 36% of those were over strong magnetic field regions, whilst 54% were over the regions where there was a weaker field. So that's telling us that the magnetic field is playing a role in that process. So unlike at Venus, the ionophores is not always well defined at Mars. At Venus, it's always there whenever you fly through that region. And we've also looked at the various pressures because we can calculate both the magnetic pressure and the thermal pressure. I won't go into the details here, but there are some interesting regions where the magnetic pressure, you can clearly see where in the strong field regions, the magnetic pressure does exceed the thermal pressure actually in the data at the lower end of the data. And we've also looked at using Aspera estimates of the solar wind dynamic pressure, which are the light blue curve in the bottom panel. You can see that the total pressure at the ionopause observations, that follows that temporal trend over a period of about 8 days during the deep dip campaign. We've also looked at cold plasma in the magnetotail. This is some work by Katerina Sturgiopoulou during her PhD thesis working with Dave Andrews. And this actually goes back to using the harmonics of the local plasma frequency. And from those harmonics, we can calculate the local plasma density. So it gives us this method of calculating this region. Now remember that we're only taking data from somewhere in this region here, in between these two green lines in the top right-hand panel. So these are the MAVEN data for a period of about 26, 27 days. You've got top panel on the left-hand side is the ion energies, from which, and that's between about 0 and, a few tens of EV up to tens of maybe 20 keV. Then you've got the moments, which give us the number density and the solar wind velocity, and from that you can calculate the dynamic pressure. Then you've got the magnetic field data, Bx, By, Bz, and at the bottom panel gives us the galactic cosmic ray intensity from the HEND instrument on Mars Odyssey, which tells us actually that there seems to be a Forbush decrease in this region over here. And this is the time at which we've got 5 orbits where we're making measurements with MARSIS on the Nightside, and those are in the right-hand panel here. The black dots, if you can just about make them out, are the estimates of the local plasma density from the summary plots that you see here from the orbit. And you can see between these two dashed lines, the spacecraft is on the night side. And you can see that there's a highly structured cold plasma in the magnetotail. It's not always there, and it's not always at the same location, but it's structured and it's highly variable. The question is this purely from transport from the day side, or is this related to other processes such as magnetic reconnection, which is enabling a channel of plasma to be created out of the ionosphere? These are things that still need to be fully understood. So we've talked about radar blackout, so I'm going to talk a little bit more in detail about that over the next 5 to 10 minutes before wrapping up. These are some data from MAVEN, from the CEP instrument. The top panel is the Electron Energies, and the middle panel, panel B, is the ion energies, and then the bottom panel shows the times of the orbits with respect to that of MARSIS, both in AIS mode, that's the pink dots and or circles, subsurface mode, the square, the blue squares, and from SHARAD, they're the black diamonds. And you can clearly see that there are times when the signal is absorbed totally by the total absorption occurs, where those each of those symbols are filled in. And from that, and using some modeling, we were able to predict that those electrons in particular would create a layer at an altitude of about 100 kilometers, peak density around about 100 kilometers or slightly below. If you then calculate the absorption, which is the bottom right-hand panel as a function of altitude, you can see that whilst the peak may be, a density may be at 100, the actual peak in the absorption occurs much lower than that, because it occurs where the radar frequency and the local collision frequency, neutral electron collision frequencies are equal. That is much lower than that, and that's around, that can be below, and that's below 80 kilometers. Note also that it's frequency dependent. So if you look at 3 megahertz, green curve, 4 megahertz, the orange curve, 20 megahertz is the purple curve, and that's much reduced. So Sharad, which operates at much higher frequencies, you would expect to see fewer events. And indeed, when we look at the statistics of these things, this is the solar cycle occurrence. MARSIS is the third panel down, and Sharad is the bottom panel. And then the top two panels are sunspot number and the solar irradiance at Mars again. And you can clearly see a very clear solar cycle variability with total blackouts tending to be more than the partial blackouts at MARSIS, whereas it's the opposite with Sharad. That's a frequency dependent aspect. If we look at the solar zenith angle distribution of all of these events, we find, interestingly, this is now the bottom left panel there, that if we plot the solar zenith angle and the probability of seeing this is just the number of occurrences in the top panel divided by the number of observations in the middle panel. You can clearly see that there's a peak in our observations around about 140 degrees, which is well on the night side. Although it looks as if we don't have that many observations, we've still got well over 1,000 observations in some of those regions, and that's a very clear feature. There's no evidence of any structure associated with crustal fields. I won't go into much detail with that for the time being. But then if we look at the electron energy-flux relationship, now this is just taking the MAVEN electron energy fluxes for 3 particular case studies, and that's just related to the top panels. Okay, the first thing, the top panel is for MARSIS blackouts, the middle panel for Sharad blackouts. So the red curve in each case is total blackout, the blue curve is the partial blackout, and the black curve is the no blackout. And the error bars there are the median absolute deviation. So clearly the fluxes are much higher for the times when there is a total blackout compared with the partial blackout, which is what you would expect. And also the partial blackout is, the fluxes are much higher than when there is no blackout. So that's very, very clear. But also we see that the fluxes are higher at all energies for the Sharad blackouts. In fact, they're higher by a factor of, quite significantly, by an order of magnitude at least, which is one of the key results from that. We also looked at another experiment, effectively, where we got solar energetic particles, but we do not have any blackout of the signal, and that's the green curve in the bottom panel. Now, this is the blue curve and the black curve are just the blue curve and black curve from the top panel replotted. And one of the key points about this is that you can see that the major difference there is the higher energy particles. The lack of the higher energy particles may in fact be the cause of the fact that we don't see the blackout. So what that's saying is higher energy particles are most likely the cause of the blackout in that case, which is what we may well have expected. So are there other events which we could use? Again, looking at the MAVEN era, and really what we're looking for is something on the night side. Now, this is the event that we looked at. This is These are the data for the whole period that we looked at for those statistics. And there is an event in December 2014 that fits these criteria. And the reason for looking on the night side is, can we see evidence of the ionospheric layer? So this is the data again for the radar blackout, December 2014. And the most important thing here is that there are far more of these MARSIS orbits. These are the pink and green data points here. Fewer Charad blackouts, but in a way that's good because in a way that means that we can just focus on the AIS data, which is what we're doing. So do we see evidence of these blackouts in the, what is it that we see? Well, this is just using fixed frequency as a function of time for 3 different orbits, no blackout, total blackout, partial blackout. And you can see that it is very, very clear that there is, that you do lose that surface signal. The loss of the surface signal here, by the way, is probably related to the fact that the spacecraft is actually going through into and outside of the Martian system. We're still not sure about that. So are there examples of a Nightside trace? The short answer is yes, there is. Yes, or yes, there are. And these are 3 successive ionospheric traces. They look a bit scrappy. They're certainly not as nice as those original ones that you saw earlier on from Discrete. But we can use those to get at least the peak electron density. And from the median electron density of those peaks, this is the variability of the electron density. And you can see that, interestingly, the peak electron density actually is actually quite large during this time frame here. This is an oddity. We don't quite understand that. And I suspect it's got something to do with the time. This is actually quite far at a lower solar zenith angle set of observations than the others. We're still looking at that. What we do see is when this blackout when the total blackout does reoccur, it does coincide with another peak, and thereafter everything goes down. But these observations are a bit of a puzzle at the moment. But the mean density varies between about 0.5 and 3 × 10⁻⁻⁻ per cubic meter, which agrees very well with the observations, with the modeling. And these are the mean fluxes in each of the energy band. We've only looked at solar wind data. The color coding is different energies going from blue, which is the low energy, to red, which is the higher energy. And you can clearly see that this is the first orbit where we have a blackout. And this is by only looking at solar wind data, we've taken a large number of orbits out. But I've now looked at this again using magnetosheath data as well.
15 minutes left, Mark.
Okay, fine, thank you. Okay, so some closing thoughts. Okay, so there are other science highlights. High altitude electron density. Of course, we don't have to use MARSIS just down at periapsis. In principle, we can use it anywhere along the orbit, provided it doesn't impact on operations of other instrumentation. So that's something that we're looking at now as a possibility. We need to look in more detail at the Nightside density observations and get a much better handle on that. To be fair, Katerina has done quite a lot of further work on that in her thesis, which I haven't shown you here. There was in September 2014, just as MAVEN arrived at Mars, a very interesting encounter between Mars and comet Siding Spring. Probably the only time we've actually had a comet encountering a planetary atmosphere whilst being able to make measurements within the planetary atmosphere. MAVEN, most instruments on MAVEN were shut down because they were concerned about the impact of cometary dust. Mars Express did continue to operate with some of the MARSIS observations, and we got some really interesting observations which Beatrice has published on a couple of occasions. One of the things that we've noticed in our data are these solar radio bursts. These have been seen before and obviously been seen elsewhere, but we now actually have a really good catalogue of these events at Mars, and we're able to think in terms of whether we can use these data both for looking at how these things propagate through the heliosphere, because most of our observations, of course, are within 1 AU or at 1 AU. And of course, with the wealth of spacecraft such as Solar Orbiter, Parker Solar Probe, as well as Bepi Colombo and others close to the sun, this gives us an additional data point that we can use to look at these things. Catherine Regan at UCL is looking at the impact of the dust storms. There's been some publication on this, but it hasn't really been followed through. We're also looking at the use of something called the error detection and oh god, I can't remember what the C stands for now, but these are means by which every time there's an error in any of the chips, you get a count number. Oh, it's counting. This is quite interesting because we can clearly see the impact of space weather events in this. This actually is almost opening up a whole new brand new set of data sets for us, because we all of a sudden now can look for times when space weather events hit spacecraft which are not doing space weather studies. For example, Gaia, which is totally useless apart from looking at astronomy. I mean, I'm sure my astronomy colleagues would be fuming to hear me say it's totally useless, but it does give us the opportunity to make measurement, look at the impact of space weather, both on the systems, but also in terms of how they propagate out through the system, through the inner heliosphere. Iron loss at Mars, that's some work, that's a lot of work that's been done by our colleagues in Kiruna on that. Bow shock and other boundaries, we've done quite a bit of work here at Leicester, Ben Hall when he was here, and also when he was at Lancaster, and a whole host of other things. One thing that we know from our work at Earth, especially in the last 20 to 30 years, is that having networks of ground-based instrumentation and multi-spacecraft missions is that multi-point measurements of a system such as a magnetosphere and or an ionosphere is really important in order to understand not just the structure, but the dynamics and how a system evolves. When you actually think about where we are now with Mars, we have a wealth of orbiting spacecraft. We have Mars Express, we have MAVEN, two fabulous missions. The Emirates Mars Mission, which is also a wonderful mission. Tianwen, a Chinese mission. Mars Reconnaissance Orbiter, it has the Sharad data. ExoMars Trace Gas Orbiter, which has data which can be used. Mars Odyssey, the galactic cosmic rays. These are all just orbiting spacecraft. These are really important data sets that we can use. But on top of that, we also have actual ground measurements. You know, Curiosity, Mars Science Laboratory, InSight. Sadly, I think InSight is no longer with us. There's a Chinese rover, Tianwen, as well. These are also fabulous potential data sets that we can use and do use in terms of looking at ground space coordination, if you like. This is something that we've learned over the last 20, 30 years at Earth, and we're now in that position, if you like. I see our exploration of the Mars plasma system as being where we were maybe 30, 40 years ago when I first started in this business at Earth. We had nothing really planned, nothing coordinated, but things, data sets everywhere. So it's worth thinking about that. These are data from the Emirates Mars Mission, courtesy of Rob Lillis. I find these fascinating. These are images of discrete FUV Aurora. You've got three different types. The left-hand type is a relatively well understood type. It's related to the crustal fields. You can see the Aurora is in, the contours of the field are here, then you've got this region here, and they are clearly associated with those field structures. This is where you have these non-crustal field blobs. These are not features which are controlled by the crustal fields, although they do sometimes relate to them. There's no clear preference in terms of any interplanetary magnetic field data, and there's more at dusk than dawn with those. So that's still something that needs to be really understood. But the one on the right, this blows my mind every time I see it. This is an aurora that extends over thousands of kilometers, but it doesn't go round a pole. It goes from pole to equator. This is absolutely fabulous. This image, I think, I look at it and think, how the heck? And these things vary, they move, they can last for several hours. What is happening? Well, it's obviously got something to do with the whole dynamics of the system, and this is what we need to really fully understand. So how are we going to do that? Well, where are we going next? Well, Mars Express is continuing to operate. It will continue to operate at least until here, possibly till here. MAVEN is operational again until at least here. There is a NASA mission called Escapade, a very, I won't say limited mission, but it is a 2-spacecraft mission. It's been delayed, sadly, because it requires a launch vehicle, but it will be going. And there's another potential mission called MATIS, which ESA are considering for the M7 mission. It's one of 5 missions being studied at the moment, and we may well learn about that, the outcome of that later in the year. This would be the first dual spacecraft mission at Mars to determine the response of atmospheric coupling to space weather. It will actually look at both the plasma and the neutral systems with in situ and remote sensing instruments. And with that, and let's hope that ESA see sense and go down that route. With that, I will say thank you for listening, and I'm now happy to answer any questions. Thank you.